Wait a moment. Merci. All right, bonjour, I'm Palina. I'm a PhD student at Nanyang Technological University, and I'm going to talk about how we can fix vulnerabilities and bugs in smart contracts automatically. So the end result would look like this. We give our tool a condition that should always be true. And then if it doesn't hold somewhere in the code, then our tool automatically suggests the way to fix it. So here we're fixing the bug that allows stealing tokens from a decentralized exchange, and therefore it violates this property that you see on the screen, making the balance of a protocol decrease while it shouldn't. So now let me explain how that works. We've just seen an example of why we should care about smart contract bugs. So DeFi protocols store a lot of money, they work on smart contracts are code, code contains bugs. In DeFi protocols, bugs usually mean financial losses, so we want to avoid them. Also, that's Bugs Bunny, and he will accompany us in this presentation because of his name. Now let's take a look at the actual bug that cost, I think, $8 million to the protocol that had it. That is a basic transfer functionality of an ERC20 token smart contract. So how does it work? Let's say we want to transfer 5 tokens. And to do that, we record the balance of a sender, we record the balance of the receiver or recipient, we perform the transfer, and then we subtract 5 tokens from the sender balance and record that on blockchain. We also add 5 tokens to the recipient balance, and we record that on blockchain too. That's it, right? So at first glance, it works correctly, and it actually does in most cases. But I'm showing you this for a reason, and the reason is what happens when I'm trying to transfer 5 tokens to myself. So in this case, again, we record the sender balance, which is 10, that's my balance, and we record the recipient balance, which is again 10, and again is my balance. Now, when we hit send, we try to transfer 5 tokens, and then we update the sender balance, we record the result, it is now 5, but then we also add 5 tokens to the recipient balance that we have recorded before, and it becomes 15. So do you see what's happening? Well, I had 10 tokens, and now I have 15. That means that I just made 5 tokens out of thin air by trying to transfer them to myself. And of course, that's a bug. It shouldn't happen. One thing I want to say about this code is that if you're not familiar with Solidity, please take note there is a require statement. I think it's the search statement there. That's basically a conditional statement. So what it does, it checks the condition that is there. If it is true, then the execution of the function continues. If it is false, the execution of the function reverts, the transaction reverts, all the effects made on the blockchain state by these transactions are reverted. All right, so what can we do to fight bugs? First, of course, we can ask developers just not to write the buggy code. Well, that's a great idea, it doesn't work. There are also, of course, tests and verification. They probably can help us identify the bug, but even if they do, which is not always the case, they still won't fix it. So what we are trying to do here is to automate the fixing step to help the developer. We want to take the buggy smart contract that has an issue, and then we want to automatically transform that into some better fixed version. So that's a very general task. So in order to make it feasible, we need to answer 3 questions. First of all, how do we decide if a smart contract is buggy and there is something that we should do about it? Second, how do we generate a fix for a smart contract that is buggy? How do we actually perform this transformation? Finally, after we generated the fix, how do we make sure that it is correct? And correct here means that, first of all, it fixes the issue we found at the first step, and second, it doesn't introduce any additional issues, which can also happen. So let's start with answering the first question, which is how do we determine that the smart contract should be considered buggy? So apart from mainstream ways to find bugs in your code, which are testing or just looking at it really carefully, there are also automated ways to find bugs. First of all, there are vulnerability detection techniques. So they are based on patterns which are defined for some common smart contract vulnerabilities. This could be, for example, integer overflow. So what these techniques do, they have this pattern and they try to identify if the code contains this pattern. In this case, it will be considered buggy. But the main issue with these approaches is that they can't detect anything beyond these hard-coded patterns. An alternative to that is to perform property-based analysis, which tries to detect if somewhere in the code, the property that should always hold can get violated. So the property just says what the smart contract should do and what it shouldn't do. So the property that is violated by this specific example is the transfer invariant. It says that the sum of the sender and recipient balances before the transfer, and after the transfer should be the same. It shouldn't change. So in this case, the property is violated if the sender and the recipient address are the same, and we can use it as an indication that the smart contract is buggy and should be fixed. But the computer doesn't really understand this natural language property, so we need to encode it in some way that it does understand. One way to do that is to just write these simple test cases that perform a transfer and then check the property afterwards. We can, for example, write the test on the left, on the right for me, that will perform this transfer in the correct way. So the sender and the recipient will be different people, the property will hold. That is the example of the correct valid behavior of our smart contract. We can also write a second test case that will exploit the bug. So it will contain a transfer from Bugs Bunny to himself, and the property will be violated. So once we generate some fixes for our smart contract, we can run these tests on the fixed version again, and then that's how we can actually decide if the fix works. Because the failing test shouldn't fail now, after we have fixed it, and the passing test shouldn't fail either. Of course, in reality, we can't really, or shouldn't, ask the developer to write those tests. So later in the talk, we'll see how we can automate that. But for now, that will be our framework. So we'll use a property to help identify bugs in a smart contract, and we'll also use test cases we wrote to assess the fixes that our tool will generate. So now let's see how our tool is actually going to generate them. In general, whenever you fix some code manually or automatically, the fix is usually just some patch that introduces the changes to the code. So there are several ways to fix our example. One of them is to just add a restriction on the sender and recipient address, which will just not allow them to be the same. So if I wrote this fix manually, that would be it. But we are generating it automatically. So the decision we need to make is whether we want to perform that on the bytecode level or the source code level. Bytecode level has several significant advantages. So first of all, it is always available in contrast to Solidity code that might not be public. Most importantly, bytecode is what exactly being executed. It is the program that is run by the EVM, also in contrast to Solidity, which has to be processed by the compiler first, which might contain bugs, which also happened, or it might introduce some optimizations we are not aware of. So generally, using source code is less safer in that regard. But bytecode also has a very significant disadvantage. It is extremely hard to read. So that is the same statement we have also seen in the source code, and it's extremely difficult to parse it if you're a human being, not the EVM. And it is also very important that we understand the fix we are going to apply to our smart contract. It's very important that we understand what is actually happening. Therefore, our choice is to perform the repair on the source code, because it's very easy to inspect visually, and the availability question is also less important because we target our tool for the developers, so we assume they have the access to the source code they wrote. All right, so we decided that we'll work on the source code, and source code is basically text. And if you're a computer, it's very difficult to work with text because it's not very structured. So as everybody who works on source code, instead of using the actual source code, we'll use the abstract syntax tree, or AST. So that is the tree-like structure you see on the screen. It can be produced by the Solidity compiler automatically. So nodes there represent code elements. And there you can see the AST for the first line, which is an assignment, and the require statement, which is the third line. So we have an AST. We know that the program contains the bug. We want to fix the bug. Fixing the bug means changing the code. So how do we actually change the code? Well, answering this question relies on a very important observation, that even in buggy programs, most of the executions will be correct. So another way to say that is that developer gets most of the things right. Therefore, if you look at the actual buggy smart contracts, and if you compare the original version with the fixed version, you will see that the diff between them is actually quite small. It would be one line or maybe a few lines max. So a straightforward approach to search for a fix, in this case, is to just brute force our way through all the small changes we can find for this program. So we can change or mutate the code in one of the following ways. First of all, we can insert a statement. That is actually the fix we're looking for. We can do that in the AST, and then respectively in the source code. We can also replace statement or parts of statement. So let's say we want to change the sign in the require statement. We can do that in the AST and in the source code as well. Maybe that could have fixed the bug. One other thing we can do is rearrange in the order of statements. We call that moving. All right, but as good as computers are at brute forcing, checking all possible changes in this code can still be too much. So we need some way to optimize our search for the patches. And one way to do that we use is to just use some heuristics. So we looked at a lot of smart contract source code from vulnerable smart contract data sets or just actual postmortems, and we noticed that some issues are just way more common than others. So these include, for example, missing required statements, slightly inaccurate required statements, missing variable updates, and so on. So what we do is we first prioritize those patches that would fix these issues. We try to synthesize them first, and we check them first before we try to generate some other statements. So that would actually generate us some pretty good one-line fixes that are very small, but in some cases, there are more complicated issues that require a several lines fix. So in this case, we need to generate a fix with a single line first, and then we need to mutate that further. And as you can probably guess, again, that generates us a very big search space for the patches that might be hard to analyze. So we need another optimization to handle that. And in fact, program repair techniques borrow some ideas from biology and evolution to do that. So they use something that is called genetic algorithm. So what's that? Well, first we need to generate, using the strategy we have just discussed, we need to generate some initial set of patches. For example, we generate 5 random patches. Then, what we want to do, we want to select the best patches out of what we call, in evolution terms, generation 1, and then we'll mutate those best patches further, and we'll just drop the rest of them. As you can probably guess, we also need a criteria to select the best patches, and we already do that. Remember the test cases that we wrote before? We can use that to assess the quality of the patches. So as we have discussed, a good patch fixes the previously failing tests, meaning that the property will now be satisfied, and they also don't break the tests that worked previously. So using that, we can actually select the best candidates, we can move them to the second generation, and then we will mutate them further. And we'll just repeat that process until we find the best patch that satisfies all the conditions that we want. It fixes all the tests. So that is actually the patch generation technique that completes the first version of our tool. So that's good. But if you were concerned by the fact that we are only using 2 tests to assess the quality of patches, you were right. And I will see why. I'll show you, sorry. All right, so in the current state, our tool will try to take a shortcut. It will generate a required statement with an invisible condition you can see on the screen. So a variable, it checks that a variable is not equivalent to itself, which of course can never be true. It can never be satisfied. The call to this function will always revert. From the point of our tool and our tests, that actually looks like a correct fix. Because if the property holds before the transfer and then nothing happens, then the property still holds, right? That makes sense. But of course, that's not something that we can use. We want people to be able to transfer their tokens. So as you can see, we need a better way to automatically ensure that good behavior is preserved. Now, let's see what options do we have for that. OK, so first of all, we can just add more tests. That is a widely used approach, and it actually would make our approach overall work better. But as all the techniques used in tests are, the patches will be subject to test overfitting. So that's very similar to how machine learning models, they just learn the test case they are trained on instead of generalizing the behavior that they observe. Our tool will do exactly the same thing. We will just try to find a patch that is very specifically tailored to exactly the data set that we have, and it will work for these test cases that we have in our data set, but it will not generalize beyond that. It may not ever work on anything beyond these tests. One example of that in our case would be the following. So we can add a test that looks like this, where we actually perform the valid correct transfer. So the sender here is Bugs Bunny, and he transfers 6 tokens to Daffy Duck. So we can check that if Bugs Bunny does that, his balance decreases by 6 if he transfers 6 tokens. Well, a patch that could have been generated in this case would look something like this. We already know that the left side of this expression is always invalid. So it's not helpful at all, but still, because of the second clause, it will allow the execution if the value is equal to 6. So even though it would work for all the tests that we have, it's not really usable. It doesn't generalize. So you might guess that instead of tests, we need some approach that would consider all possible behaviors, not just some specific behaviors that are caused by concrete values we used in the test. And that's what we have formal analysis techniques for. And especially symbolic execution, because analyzing all possible executions of a program is exactly what symbolic execution does. Now let's see how symbolic execution works. It might be a bit too much to wrap your head around symbolic execution in one slide, but that's a general idea. So let's consider this simple program that is given on the slide. There is one conditional statement checking that x is less than or equal to y. Therefore, this program has two branches. This condition can either be true, in this case that would be equal to x, or it can be false, and that can be equal to y. So symbolic execution assumes that the variables used in this condition are symbolic. And symbolic here means arbitrary or any. That means that x and y can take any possible values that an unsigned integer, which they are, can take. Therefore, both of the branches, in this case, should be explored. They can both be true. Symbolic execution for the analyzed code memorizes or records two types of information. First of all, let's explore the true branch first. So the first type of information it collects is the path condition. It's called PC on the slide. So the path condition is just a condition, or we also call it a constraint, that represents the condition that should hold in order for this path to be analyzed. Then the other type of information is the variable updates. So whenever we execute this path, we also want to record that that would be equal to x if this condition is true. So we record this, the path condition first, that x is less than or equal to y, and the variable update. Then we also repeat this process for the false branch, and that pretty much gives us a comprehensive view of how the program actually can work with. So these are the only ways it can be actually executed. So what happens if we symbolically execute our example? So for simplicity, let's assume that Bunny is always the center. It will limit the number of paths that we have in this presentation. And the recipient can either be Bugs Bunny or it can be Daffy Duck. Val corresponds to the amount being transferred, and it can be any unsigned integer. So since it can be any unsigned integer, when we symbolically execute the program, we record some variable updates. But then, once we reach the required statement, we know that both of the cases are feasible. So either the required statement is true and the execution of the function continues, or it is false and the transaction reverts. So then, if it didn't revert, then we continue updating some variables. We record that information in the symbolic execution tool state as well. And then we also need to check the assert. So we already know from our previous discussion that the property can either hold, in this case, if the sender and the recipient are different, or it can also fail, so the property may not hold if the sender and the recipient are the same address. Then, then from the previous discussion and our manual analysis, we also know that if the transaction reverts, then the property will just always hold. So we do know for sure from our manual, again, analysis, that this condition is not possible. So it's not feasible in our example for the transaction to revert and the property to be violated. But we know that, and the computer doesn't know that. So since we're trying to automate this whole approach, what we want to do is to inform computer about that as well. So what we can do for that is to use an SMT solver. So without going into the details, SMT solver can be viewed as a tool into which we can feed these conditions, the path conditions, so these constraints that we have, that balance should be less than val and that the property is not holding. And then we can use the SMT solver to ask it, can these conditions be satisfiable? In other words, that means, can this ever be true? In this case, SMT solver tells us that no, it's not possible. That is unreachable, no point in analyzing this further, we just drop that. But we still have these three other execution paths with their path conditions that we can analyze. So we also invoke the SMT solver to check their satisfiability, and they are satisfiable. So all of this can actually happen. So a very exciting feature of an SMT solver is that it can generate concrete values for these satisfiable path conditions that symbolic variables should take in order to drive the execution towards a specific execution path. So we can use that to generate test cases automatically. However, we already have seen that using test cases might be insufficient. So we need a more formal way to actually prove that the original behavior that was valid and the behavior of a patch smart contract, they're actually equivalent. And that is one more thing that we can use an SMT solver for. So in a very similar manner, as we use the SMT solver to check if these conditions are satisfiable, we can also ask the SMT solver, is program 1 equivalent to program 2? So that's what we are going to do for our original and fixed smart contracts. So in order to use an SMT solver to do that, we need to actually try to check the opposite. So we write a condition saying that the original smart contract is not equivalent to the patched smart contract. Then we can ask the SMT solver, is that satisfiable? And if that is satisfiable, it means that the SMT solver managed to find some concrete values for which the programs behave differently, meaning that they're not equivalent. In contrast to that, if it couldn't find any solutions, it means that they behave exactly in the same way. They're equivalent, we found our fix, that's it. But the issue is, SMT solver doesn't understand solidity. So we can't just fit that into the SMT solver. What we can do instead is to translate it into something that SMT solver does understand, and that is logical formulas. So we just need to take that and translate it into a logical formula. The logical formula should just encode all the behavior, the whole behavior of this function. So in other words, it should summarize that. We would call it summary. Since we already have analyzed the 3 possible execution paths of the contract, we already know exactly what's going to happen in each path. So we just need to combine this information about individual paths into one big formula that will fit the SMT solver. So the formula should convey the following idea. There are 3 ways in which this function can be executed. Either the required statement is satisfied and the property is satisfied as well, or the required statement is satisfied, the property is violated, or we just revert. That's it. So that's exactly what we're going to build in a formula. So I don't want to show actual formulas. They are unreadable. So just imagine there are formulas in these rectangles. So first of all, we of course want to collect some information about how the variables are updated. Then, when we see a require statement, we know that there are 2 possible ways in which the program is going to be executed. So we split that into 2 clauses. It's either true or it is false. If it is true, then there are some more variable updates that we also recorded in the summary. And then we check the assert, which again splits the first clause into 2 possible ways, as we have seen before. That is a summary. Then we can repeat the same process for the patch smart contract. It is a bit different. It now has a new line of code, so the summary will look in a slightly different way. But if out of those summaries, we only choose the parts which correspond to these valid behaviors from the original program we want to preserve, and then ask the SMT solver are they equivalent, then it will tell us that yes, they're equivalent. In fact, that is one of the fixes for this program. All right, so that's the final state of our framework for today, which now has symbolic execution, automated test case generation, and equivalence checking. So you might be wondering why we're still using test cases if we have equivalence checking. And the answer is because equivalence checking is very computationally expensive. So we can use test cases to just quickly remove the patches that obviously don't work. These are just some examples of what we can do with that. So first of all, we have already seen that. We can automatically change the constant to the correct one in the require statement. We can generate some require statements like access control, which before we added that, this code violated the property that the owner can only be changed to a code that was provided by the previous owner. And we can also fix something a bit more complicated, such as, for example, the following property for the pool smart contract, where you could send your tokens to stake them. So there was one type of token that had an address, which you could stake there, and it should have never been changed in this pool. But you could reset this value in the initialize function, which was supposed to be only called once. But someone forgot to set the flag that it has been initialized to true, so you could have reset this value, but you can't anymore if you have fixed that. All right, so that basically concludes my presentation. The short summary is that we can fix bugs in smart contracts automatically. We can do that in practice. We can do that using formal techniques that can be used for to solve other problems beyond verification, as there usually is. Yeah, on a side note, we are setting up a spin-off startup company to commercialize the research in this direction, and we're focusing on the builder-first approach to security. We are currently raising funds, so if you're interested, please drop me a line to this email address, and there is also my Twitter account in case you need anything else too. All right, thank you very much.
Any questions?
Thanks. Have you explored other techniques to prune the results, like for example using fuzzing to compare different implementation and do, for example, differential fuzzing to check if the implementation are more or less the same?
Oh yeah, I think you can use exactly what you said. Differential fuzzing should help. The only thing is that if you're using these formal techniques, if you're using formal verification, SMT solvers to do that, you have somewhat better security guarantees because potentially you're covering like the complete behavior. It's very exhaustive. On the other hand, it of course comes with scalability issues. So if you have loops, or if your program is just very complicated, or if you want to, for example, build a summary for several functions in a row, that won't really work that well.
Can I ask some question? Okay. How do you deal with the initial state for the symbolic execution engine? Because in this example, you have like one function, but how do you deal like if the function with a state variable or stuff like that?
Well, you mean if we have several functions in the execution trace?
Yeah, like you have a function with a bug, and within this function, you are going to read a state variable, and the value of the state variable might depend on previous call or like something else. How do you deal with that?
Well, so this particular function did change some state variables. So we just record that into the summary, and we assume that the value for correct path, the value should just not change for the state variables.
Okay.
But yeah, so the issue here is that what do we do if our execution trace that leads to the vulnerability has several functions, and they all have state variables that we update, they call each other. Yeah, so that's, in all the examples that we had just a few functions.
Okay.
So it wasn't that long, and there were not that many variables, so we could just mutate that using this technique, and it actually did work it worked pretty fast. It was, I think, sub-minute time or something like that. But then, of course, theoretically, that is a bottleneck. That's true.
Thanks. It's really interesting work.
Thank you very much.
Hello. Thank you for the presentation. So I was wondering, how do you carry new version of a language with your solver? So imagine there is a new version where it's not the same semantic. So how do you carry that?
Oh, we do the same thing as, so here I had an example of how we build this summary for the original version, right? And then we just repeat the same process for the patched version. So we just symbolically execute it once again. We again build a summary for that, and that's it. So, and then we just ask the solver if these are equivalent, and the solver can infer if they are, even if they look slightly different.
And it's the same for in Solidity 8 and before. There is overflow that is not carried with the compiler. So it's like the same?
Yeah, so honestly, we do this on Solidity 0.5. So we have our own symbolic execution engine that is Solidity level, and it currently works with 0.5, but I think we are porting it to other versions as well. There are slight differences in semantics, so we'll just encode that information in the summary if there is some.
Okay, thank you.
Thanks. All right, well, thanks a lot.